안녕하세요. 글로벌 인공지능 대표 컨퍼런스 AWC 2022인 부산에 오신 것을 환영합니다. 저는 어제에 이어 A홀 사회를 맡고 있는 인공지능 전문 매체 더 AI 편집국장 전승민입니다. 반갑습니다. AWC 2022인 부산 2일차에서는 어제에 이어 더 굿 AI 캔두라는 주제로 국내외 인공지능과 미래 기술 전문가분들의 더 많고 더 다양한 강연과 패널 토론을 들으실 수 있겠습니다. 오늘 행사는 동시 통역 서비스를 제공하고 있습니다. 한국어 1번, 영어 2번으로 들으실 수 있습니다. 고맙습니다. 그럼 본격적으로 인공지능 기술의 혁신과 미래를 제시하기 위한 AWC 2022인 부산 2일차 일정을 시작해 보겠습니다. 첫 번째 순서로 저희가 굉장히 어렵게 모셨습니다. 정명훈 구글 코리아 파트너 엔지니어링 리드 분께서 자리해 주셨는데요. 구글의 AI 칩 전문가 분이시고요. 오늘 앞으로 AI 학습에 필요한 컴퓨터 자원이 급속히 증가하고 있는데 여기에 대해서 어떻게 우리가 해결책을 가질까에 대해서 많은 좋은 말씀 들어보도록 하겠습니다. 무대로 모시겠습니다.
네, 안녕하세요. 정명훈입니다. 네, 백신을 다 맞았기 때문에 마스크를 조금만 내리고 얘기를 하겠습니다. 이렇게 좋은
전달을 위해서 강의자분은 마스크를 벗고 진행해 주셔도 괜찮을 것
감사합니다.
같습니다. 네.
제가 오프라인 발표를 이제 코로나가 좀 완화되면서 오프라인 발표를 많이 하게 되는데 마스크를 쓰고 하면 정말 답답하기도 하고 또 좀 제 발음이 이렇게 좋지 않다 보니까 전달도 잘 안 되는 경우도 많더라고요. 일단 이렇게 좋은 자리에 초대해 주셔서 정말 감사드리고요. 제 소개에 보니까 이제 미국이라고 괄호를 그렇게 써놓으셨는데 원래 미국에서 온 건 아니고 한국에 있는 구글 코리아에서 지금 현재 근무를 하고 있고요. 주로 이제 클라우드 파트너 엔지니어링 쪽, 그 다음에 AI 머신러닝 쪽 엔지니어링을 담당하고 있습니다. 오늘 제가 발표할 내용은 이제 발표 요청을 받고서 좀 고민을 하다가 구글 하면 아시는 것처럼 이제 AI를 많이 하는 회사잖아요. 그래서 구글의 많은 AI 얘기 중에서 어떤 걸 하면 좋을까? 자율주행차, 아니면 자연어 처리, 버트나 이런 것들, 유튜브에 무슨 추천 알고리즘 이런 것들도 많이 고민하다가 조금 이제 덜 발표했던 내용들 한번 골라봤어요. 요즘에 이제 초거대 AI라고 하는 이런 흐름이 있다 보니까 거기에 좀 도움이 될 만한 내용으로 구글의 TPU 약자로 텐서 프로세싱 유닛이라고 하는데요. 이제 구글의 AI 전문 칩이에요. 그래서 이 구글의 AI 전문 칩인 TPU에 대한 얘기를 제가 세 가지 관점에서 설명을 드리려고 하고요. 첫 번째는 이제 구글의 AI 칩은 TPU라고 얘기를 하고 있고 저희 내부적으로도 많이 쓰고 있고 또 구글의 이제 고객분들께서도 사용을 하고 계시고요. 두 번째는 이 AI 칩이 이제 어떤 식으로 그러면 AI 모델들을 AI의 모델 학습이라든가 이런 부분들을 도울 수 있는지에 대한 얘기를 잠깐 설명드리고요. 궁극적으로 초거대 AI가 하이퍼스케일 AI가 돌아가기 위해서는 결국 이 AI 모델을 학습하는 데 필요한 컴퓨팅 자원이 스케일러블하게 증가해야 되는데 그런 부분들이 어떻게 돌아가는지 그 세 가지를 가지고서 설명을 드리겠습니다. 먼저 이제 구글의 TPU가 어떤 이유에서 나오게 됐는지, AI 전문 칩이라고 하는 게 왜 필요한지를 한번 얘기를 해볼까 하고요. 그 과정에 자연스럽게 구글의 AI 히스토리를 한번 얘기를 해보겠습니다. 일단 일반인들에게는 많이 알려져 있는 이벤트가 역시 구글의 이제 알파고 이벤트예요. 국내 같은 경우는 특히나 되게 임프레시브했었죠. 저도 저 당시에 한 2016년으로 기억하는데 저도 저 당시에는 사실은 이제 아마도 이세돌 기사님이 알파고를 이길 것 같다라는 예상을 했었어요. 저도 솔직히. 왜냐하면 그 당시만 해도 딥뉴럴 네트워크가 그렇게 발전하기 전이었고 AI가 그렇게까지 발전했을 거라고 생각하지 못했었어요. 그래서 사실은 이제 여러분들이 아시겠지만 이런 알파고 같은 이런 알파고를 통한 이세돌 기사와의 대국은 사실은 AI 기술이 이렇게 발전했어라고 하는 거를 보이기 위한 이벤트거든요. 하나의 이벤트거든요. 그러니까 뭐 저희 어렸을 때 또는 이제 뭐 여러분들 자녀분들이 계시다면 자녀분들이 열심히 배우고 한 거를 한번 설명할 때 뭐 학예회 같은 걸 해서 설명을 하잖아요. 말하자면 그런 이벤트인 거죠. 그 이면에는 그걸 위한 여러 가지 과정들이 있었을 것이다라고 하는 거고요. 사실은 이제 저 그 알파고 이벤트가 되기 전에 이미 구글에서는 이제 구글 X라고 하는 소위 말하는 뭐 UFO도 만든다고 하는 구글 X 팀의 조프리 힌튼 교수님이나 아니면 스티브 교수님 같은 분들이 이미 계속 딥뉴럴 네트워크를 공부를 했었죠. 그리고 딥뉴럴 네트워크가 많이 어려웠던 부분들, 뭐 백프로퍼게이션이라든가 이런 부분들을 해결을 하면서 결국은 딥뉴럴 네트워크가 어느 일정 수준으로 올라왔어요. 그죠? 지금은 사실 초반에는 딥뉴럴 네트워크가 어떤 거고 이런 설명을 다 하지만 지금은 그냥 DNN이다라고 하면 거의 일반 명사처럼 돼버렸죠. 그렇게 된 과정이 사실은 저런 많은 분들이 일을 하셨던 거고, 오늘날 이제 AI의 그 근간이 되는 게 딥뉴럴 네트워크인데, 딥뉴럴 네트워크는 사실은 이제 데이터 기반으로 돌아가게 되잖아요. 많은 양의 데이터가 없으면 돌아갈 수가 없거든요. 그 데이터를 모으는데 일조를 하셨던 분이 여기 그 사진에 나와 있는 이제 페이페이라고 하는 분, 이미지넷을 만드신 분이에요. 구글에서 이제 VP로 일을 하셨고, 구글에서 VP로 하시기 전에 이제 본인이 직접 많은 그 팀원들과 함께 이미지넷이라고 하는 데이터를 모아서 사실은 그 데이터 덕분에, 그러니까 딥뉴럴 네트워크가 데이터가 결합이 되면서 이제 성과를 내기 시작했던 거죠. 네. 그래서 이제 아시는 것처럼 알파고를 만들었던 데미스 허서비스 같은 이런 분들이 이렇게 얘기를 했다 그래요. 네. 딥마인드 같은 것들이 결국은 AI 업계에 어떻게 보면 이제 아폴로 프로젝트 같은, 달 착륙하는 그런 프로젝트 같은 느낌이다. 이 의미를 잘 생각해 보면 아폴로 우주선이 아폴로 11, 우리가 기억하고 있는 이제 달 탐사는 아폴로 11호 우주선이 달에 착륙해서 닐 암스트롱이 내린 그 장면만 기억하죠. 그래서 사실은 그 전에 이미 아폴로 1호부터 해서 수많은 로켓들이 달에 궤도를 돌고 착륙 시도를 하고 하다가 그 첫 발자국이 사실은 11호의 닐 암스트롱이었던 거잖아요. 마찬가지로 딥뉴럴 네트워크가 데이터가 모이면서 근간이 준비가 된 거고, 그게 어느 날 갑자기 이제 알파고 같은 이벤트를 통해서 일반 대중들이 훨씬 더 이해하기 쉽게 드러났던 거죠. 네. 그래서 사실은 구글의 많은 서비스들, 유튜브, 검색 엔진, 또는 트랜슬레이트, 번역, 네, 뭐 자율주행, 이런 부분들이 내부적으로 많은 AI 서비스들이 돌아가고 있어요. AI 서비스가 없다면 사실은 구글의 서비스가 오늘날처럼 이렇게 많이 사용이 되지 않았을 거예요. 유튜브 한번 보기 시작하면 추천 엔진을 통해서 계속 보고, 네, 그런 일들이 생기죠. 특히나 구글의 이제 가장 기본적인 그 서비스는 검색이잖아요. 최근에 검색을 해보신 분들은 느끼겠지만, 저도 구글 검색을 많이 하는데 좀 틀리게 입력해도 조금 어느 정도 힌트만 줘도, 네, 또는 의문을 던져도, 질문을 던져도 답을 주죠. 그런 부분들이 사실은 뒤에서 AI가 동작을 하고 있는 거거든요. 최근에 구글 검색 엔진의 개선을 가장 많이 이룬 요소는 결국은 AI 엔진이에요. 그 덕분에 구글의 검색 엔진이 이렇게 스마트해진 거죠. 네. 그래서 이렇게 이제 구글의 AI 얘기를 드렸고, 그 다음에 두 번째로 이제 아까 서두에도 말씀드렸던 초거대 AI, 하이퍼스케일 AI에 대한 얘기를 좀 해볼까 합니다. TPU와 연관이 있어요. 요거는 이제 구글이 발표했던 트랜스포머라는 논문에서 했던 아주 인공지능 하는 사람들한테는 유명한 키워드죠. Attention is all you need. 예, attention만 있으면 모든 것들이 해결된다. 자연어 처리에 거의 혁명적인 이제 변화를 이뤄냈죠. 그 덕분에 뭐 버트도 나오고 GPT-3 같은 모델도 나와서 오늘날은 자연어가 너무나 자연스럽게 돌아가고 있죠. 번역도 너무나 자연스럽게 되고 있고, 뭐 예전에는 예를 들어서 번역을 할 때 번역기 돌렸어? 이런 농담을 한다면 지금은 번역기가 오히려 저보다 낫더라고요. 네. 그런 시대를 사실은 이제 구글의 리서치팀이 만들었던 트랜스포머라는 논문을 통해서 만들었는데, 보시면 이 자연어 처리가 급격히 발전을 하면서 보시는 것처럼 오늘날 뭐 어떻게 보면 이제 가장 크다고 알려져 있는 GPT-3 같은 모델은 내부적으로 이제 머신러닝 그 모델의 노드 혹은 이제 외부에 많이 알려져 있는 말로 이제 파라미터라고 표현을 하는데, 그 파라미터의 개수가 예전에는 이렇게 뭐 120만 개 이렇게 갔다면 어느 날 갑자기 1,700억 개의 파라미터가 있는 이제 모델로 발전한 거죠. 그래서 GPT-3를 이용하면 정말 뭐 내가 물어보는 모든 걸 답을 할 수 있고, 내가 원하는 글도 작성해 줄 수 있고, 뉴스 기사를 요약해 줄 수 있고, 이런 것들이 된다고 하죠. 그게 저만큼 자연어 처리 기술이 계속 발전하고 또 모델이 커진 거죠. 예, 커진 거죠. 그리고 그러다 보니까 자연스럽게 해외뿐만 아니라 국내의 많은 기업들도 LG라든가 네이버라든가 카카오, KT, SK 같은 기업들도 비슷한 수준의 규모의 초거대 AI에 도전을 하고 있어요. 파라미터 수를 보시면 이미 GPT-3를 넘어섰죠. 네, 어마어마한 규모라는 거예요. 상상도 사실 잘 안 가요. AI 머신러닝을 직접 코딩하고 초창기부터 해보신 분들이라면 아마도 뭐 노드의 개수가 몇백 개, 몇천 개 이 정도만 가지고도 학습할 때 엄청나게 많은 시간을 들였는데 3천억 개라고 하는 거는 감이 잘 안 오거든요. 그리고 구글 역시 구글 스케일이죠. 1조 6천억 개의 파라미터를 튜닝한다. 어느 정도의 컴퓨터가 필요할까요, 과연? 네. 그래서 AI 머신러닝 모델이 여기는 이제 시간축이고요. 연도를 나타내는 거예요. 연도별로 계속 발전을 하는데 중간에 이제 뭐 이미지넷 챌린지 같은 그런 것들이 들어있을 텐데 이렇게 연도별로 머신러닝 모델은 계속 발전을 하고요. 알파고가 여기 있는데 사실은 그 이후에 버트라던가 뭐 GPT-3 같은 그런 모델들이 더 있어요. 여기 가려져 있지만 컴퓨팅 파워의 증가를 보시면 이게 그냥 단순 스칼라 증가가 아니고요. 그 로그 사이즈, 즉 익스포넨셜한 증가를 나타내는 거예요. 그러니까 이게 하나의 요 칸이 10배씩 증가하는 거예요. 그 얘기는 머신러닝 모델이 발전하고 머신러닝 모델이 점점 사람하고 비슷해지고 사람이 하는 일을 거의 대신할 정도 수준으로 증가함에 따라서 컴퓨팅 파워는 익스포넨셜하게 증가하더라. 그 속도가 어느 정도냐? 매달 3개월 반에 한 번씩 머신러닝에 필요한 컴퓨팅 파워가 2배가 증가한대요. 2배가 증가한다. 익스포넨셜하게 증가한다. 어디서 많이 들어봤던 얘기 아닌가요? 네. 옛날에 많이 봤던 반도체의 집적도는 2배가 늘어난다는 무어의 법칙이죠. 근데 많은 분들이 얘기하죠. 무어의 법칙은 이미 깨졌다. 예. 하드웨어의 성능 향상은 한계가 있는 거고 그 한계점이 이제 세츄레이션 되면서 점점 이제 그 증가는 따라오지 못해요. 모순되죠, 지금. 모순되죠. 하이퍼스케일 AI, 초거대 AI가 필요하고 컴퓨팅 파워는 익스포넨셜하게 증가하는데 실제 하드웨어의 발전 속도는 더 이상은 따라갈 수 없다. 최근에 삼성전자가 그 뭐 3나노 공정, TSMC가 3나노 공정 얘기를 하면서 3나노 공정을 가니까 이제 양자역학이 나오더라고요. 예, 양자도약에 의해서 너무 회로 선폭이 얇다 보니까 갑자기 회로 다른 선으로 넘어 뛰는 거예요. 그 정도로 하드웨어적으로 이거를 집적화하기에는 한계가 있는 거거든요. 근데 인간은 언제나 솔루션을 찾죠. 방법을 바꾸면 되겠다라는 생각을 하는 거죠. 그리고 이제 이분은 제프 딘이라고 구글의 그 시니어 펠로우 엔지니어라고 이제 이시고요. 그리고 여러분도 잘 아시는 텐서플로우를 만드신 분이에요. 물론 이분이 혼자 만드신 건 아니지만 같이 만들었지만 이분이 이제 팀을 이끌고 텐서플로우를 만들었는데 이분이 한 2014년, 15년 정도 했던 얘기가 있어요. 어떤 얘기가 뭐였냐면 구글이 구글 어시스트 같은 이제 어시스턴트 같은 음성 인식 기능 있죠. 또는 요즘 우리가 외국에 나가서 뭘 영어야 뭐 다 잘하시니까 영어를 하면 되지만 영어가 통하지 않는 나라에 가서 말을 할 때 가끔 구글 트랜슬레이트 앱을 켜고 그걸로 대화하는 경우도 많죠. 그런 식으로 만약에 구글 안드로이드를 쓰는 사람들이 음성을 3분씩만 입력하면 구글의 데이터 센터는 물론이고 전 세계에 있는 모든 데이터 센터를 다 써도 불가능할 거다라는 거예요. 왜냐? 앞에 설명드렸잖아요. 머신러닝 모델이 필요한 컴퓨팅 리소스는 익스포넨셜하게 증가한단 말이에요. 근데 하드웨어는 그걸 못 따라가기 때문에 그런 방식으로는 안 될 거야 라는 거예요. 그래서 저희가 생각한 게 바로 제가 오늘 설명드리고 싶은 TPU인 거예요. 일반적인 프로세싱 엔진에 비해서 뭐 최대 30배까지 빠르고, 이게 단지 반도체의 집적도를 높여서 해결하는 방식이 아니란 거죠. 그게 어떤 방식인지 뭐 오늘 학술회의가 아니기 때문에 제가 다 설명드릴 수는 없겠지만 알기 쉽게 원리 면에서 설명을 드리겠습니다. 자, 그러면 구글의 TPU에 대한 얘기를 잠깐 드려보겠습니다. 우리가 알고 있는 이제 머신러닝에 필요한 그 컴퓨팅 자원들을 생각해 보시면 CPU, GPU, 그리고 제가 오늘 얘기할 TPU, 또는 이제 구글의 TPU 말고 구글의 TPU 이후에 최근에 뭐 NPU라는 용어를 통해서 뉴럴 네트워크를 처리할 수 있는 프로세싱 엔진들을 만들기 시작했어요. 근데 어쨌든 그 프로세스들이 위치하는 포지션을 보시면 CPU라던가 이런 이제 라이트한 장치들은 주로 머신러닝을 인퍼런스, 그러니까 프리딕트 하는데 주로 사용 많이 하죠. CPU를 통해서도 프리딕트를 많이 하죠. 이거 가능한 거고요. 일반적인 머신러닝도 기존의 GPU라던가 이런 것들을 통해서 충분히 가능하다는 거예요. 근데 오늘 제가 설명드리고 싶은 초거대 AI가 되게 되면 조금 더 강력한 컴퓨팅 파워가 필요할 거다라고 하는 거예요. 거기에 구글 TPU가 일조를 할 텐데, 제가 서두에 구글 TPU에 대한 얘기를 세 가지 관점에서 설명드린다고 말씀드렸어요. 첫 번째는 AI 칩이다라고 하는 말씀을 드렸고요. 두 번째는 왜 AI 칩이 빠르게 동작할까라는 얘기를 설명드릴 거고요. 세 번째 얘기가 사실은 더 중요해요. 스케일러블하게 증가되는 게 중요하거든요. 그러니까 한 명이 일을 하는 것과 10명이 일을 하는 건 다르잖아요. 그래서 어떻게 하면 이 AI 칩이 하나가 아니라 100개가, 1000개가 동작했었을 때 리니어하게 성능을 증가시킬 거냐, 그런 얘기를 이제 하고 싶은 거죠. 그래서 일반적인 인퍼런스, 머신러닝, 초고대 AI로 가게 되면 병렬 컴퓨팅이 중요한, 또 병렬 컴퓨팅이 성능 저하가 없는 그런 스케일러블한 컴퓨팅 파워가 필요하다라고 하는 얘기입니다. 그래서 잠깐 이제 우리 그 컴퓨터 사이언스 시간으로 잠깐 돌아가 보시면 CPU와 GPU 그리고 TPU를 잠깐 이제 비교를 해봤어요. CPU는 우리들이 많이 알고 있는 그 펀더멘털 아키텍처에 기반해서 돌아가고 있죠. 컨트롤 유닛이 있고요. 그 안에 계산기 ALU가 들어있고, 그 계산을 위해서 메모리에서 데이터를 가지고 와서 계산을 하고 다시 외부 아웃풋 디바이스로 출력을 하죠. 그게 일반적인 CPU의 동작 모델인데, 이 CPU는 복잡하고 다양한 일을 할 수 있게 만들어 놨어요. 여러분들 다 아시는 얘기예요. 복잡하고 되게 어려운 일을 할 수 있게 해놨고, 그걸 통해서 정말 뭐 지난 한 20년, 30년 동안 엄청난 발전을 이뤄냈죠. CPU 기술을 통해서 워낙 많은 일을, 워낙 다양한 일을 할 수 있으니까. 다만 이 CPU에 돌아가는 요 중간에 들어가는 계산 처리 로직 또는 컨트롤 유닛, 이런 것들이 너무 좋은 거죠. 너무 좋은 거죠. 그러다 보니까 우리가 알고 있는 CPU의 코어 개수가 많은 거는 아마 많은 건 아마 한 16코어 정도까지 들어본 것 같아요. 저도 개인적으로 8코어, 4코어 이렇잖아요. 그러니까 CPU가 워낙 좋은데 CPU가 동시에 처리할 수 있는 이 계산 장치가 대략 8개, 16개가 들어있다는 거고, 그런데 그렇게 하다 보니까 그래픽 처리 같은 경우에는 워낙 픽셀 연산이 너무 많은데, 뭐 3D 게임 같은 걸 하게 되면 픽셀 연산이 엄청 많은데, 이 픽셀 연산은 CPU처럼 한 번에 4개, 8개를 계산하는 게 아니고 수천 개를 계산하더라 이거죠. 그러면 그 수천 개의 계산을 위해서 굳이 CPU 같은 고급스러운 장치가 필요할까? 아니죠. 좀 더 단순한 그냥 부동산 수점 연산만 할 수 있는, 정말 단순한 일만 할 수 있는 ALU를 여러 개 만들어서 그 코어를 엄청나게 많이 배치하죠. 그래서 CPU랑 비교를 해보시면 CPU는 이렇게 ALU 장치들이 좀 고급스러운 장치들이 이렇게 몇 개 들어있다면, GPU에는 뭐 많은 거는 지금 3000코어, 4000코어, 제가 알기로는 그 정도 되는 걸로 알고 있어요. 그렇게 많이 들어있죠. 딱 비유를 해보면 그런 거잖아요. 그러니까 대학생과 성인들과 중학생들을 비교하자면 당연히 복잡한 업무 처리는 대학생, 성인들이 잘하지만 단순한 수학 계산을 1000번을 해야 된다. 그 경우면 당연히 중학생들이 잘할 거잖아요. 그래서 그런 역할을 하는 게 GPU가 여러 가지 이제 작은 ALU들을 모아서 코어를 여러 개 만들어서 동시에 계산을 여러 개 하는 방식이에요. 여기까지만 해도 머신러닝의 사실은 AI 머신러닝의 브레이크드루였었죠. 정말 그 AI 머신러닝을 많이 발전시켜 왔었죠. 그런데 거기서 좀 더 나가 보면 AI 머신러닝에서 딥뉴럴 네트워크에서 계산하는 계산의 대부분이 저런 실수 연산이지만 실수들을 어떻게 계산해요? 행렬을 만들잖아요. 매트릭스를 만들어서 매트릭스 계산을 하거든요. 그러면 GPU 입장에서는 매트릭스 계산에 필요한 예를 들어서 10x10이면 100개의 연산을 한 번에 빵 시키고 결과를 다시 또 꺼내서 그거를 다음에 다 합산을 시킨다든가 이런 식의 과정을 거치는데 TPU를 대표로 하는 이런 그 AI 전문 칩들은 행렬 연산 전체를 그냥 하나의 오퍼레이션으로 해버리는 거죠. 연산 과정에 들어가는 여러 가지 데이터를 주고받는 과정도 이런 거 다 생략하고 행렬을 그냥 통째로 넣어버리면 통째로 계산을 해서 하나의 오퍼레이션으로 그냥 끝내버리는 거예요. 우리가 알고 있는 CPU 클럭 뭐 1GHz, 2GHz, 3GHz면 그 클럭 사이마다 일반적인 GPU나 CPU는 한 번에 부동소점 연산이 일어난다면 이 TPU는 한 번에 행렬 연산이 한 번에 한 클럭이 일어나 버리는 거예요. 그러니까 빠를 수밖에 없고 그 행렬의 연산에 필요한 여러 가지 통신들 이 노드들마다 얼마나 서로 통신을 하겠어요. 행렬의 전체 계산을 다 모아야 되니까 그것들이 다 고속 링크를 통해서 연결되어 있어요. 그러니까 행렬 연산이 한 방에 빵 일어나는 거예요. 그러니까 빠를 수밖에 없죠. 근데 여기까지는 사실은 이제 GPU도 GPU도 이런 기술들을 넣고 있어요. 그러니까 엔비디아의 그 V100 시리즈 같은 경우에는 그런 이제 행렬 연산을 좀 할 수 있게 텐서코어라는 기능들을 넣어서 그런 기능들을 조금씩 하고는 있어요. 그 다음 부분이 이제 스케일러빌리티의 문제인 것 같아요. 구글의 TPU는 하나의 그 보드가 4개의 칩으로 구성이 되어 있어요. 이 4개의 칩을 하나로 묶어서 이 보드를 만드는데 이 보드를 보시면 밑에 보시는 이 칩의 이 숫자 128, 256, 512, 1024가 칩의 개수예요. 칩을 500개, 1000개를 묶어서 병렬 컴퓨팅을 한다는 말이에요. 자, 한 명이 하는 일을 10명이 하면 당연히 빨라져요. 그런데 실제로 해보면 어때요? 한 명이 하는 일을 10명이 하다 보면 10명 사이에 커뮤니케이션이 걸린단 말이에요. 커뮤니케이션 오버헤드가 생겨요. 그걸로 인한 성능 저하 때문에 실제로 10배가 나오지 않아요. 근데 구글의 TPU가 128에서 256으로 늘어날 때 대략 2배 늘어나죠. 성능이 2배 늘어나죠. 512로 대략 2배 늘어나죠. 1024로 완전히 2배는 아니지만 대략 2배가 늘어나죠. 이게 중요하다는 거예요. 기본적으로 머신러닝에 필요한 행렬 연산을 빠르게 할 수 있다. 근데 초고대 AI는 그런 연산이 행렬 계산이 10개, 20개가 아니잖아요. 몇 천억 개이잖아요. 그러다 보면 그게 스케일업을 해야 되는데 그런 부분들이 어느 정도 이렇게 리니어하게 증가할 수 있다 이 얘기예요. 지금 여기는 1024라고 뒀지만 이게 2048이 되고 4096이 되면 그만큼 대략 2배, 대략 4배로 증가한단 말이에요. 그러니까 초고대 AI를 만들 때 빠르게 머신러닝 모델을 학습할 수가 있겠죠. 그래서 기본적으로 이제 저희가 TPU를 버전 1부터 계속 만들고 현재 이제 버전 4까지 나왔는데 버전 3 시절에 대략 TPU 그 버전 3를 1024개를 모은 요 전체를 하나의 파드라고 불러요. 파드 전체를 묶어서 이 파드 자체가 다 고속 링크로 다 연결이 돼 있어요. 최근에 여러분들 왜 그 애플에 M2 칩이 나오면서 재밌는 걸 하죠. 칩이 하나 있는데 이 칩을 2개를 붙이면 성능이 2배, 4개를 붙이면 서버급 이렇게 하죠. 그러니까 칩은 하나인데 그걸 붙이면 병렬 처리를 통해서 빠르게 되어 있어요. 다른 회사는 왜 못할까요? 그 칩을 설계할 때부터 2개를 붙였을 때 원활하게 통신이 되게 고속 링크를 만들어 놨거든요. 마찬가지로 TPU가 그렇게 1024개의 칩이 붙어도 고속 링크가 될 수 있게 만들었기 때문에 이게 이제 10만 테라플롭스 정도의 성능이 나온다라는 거예요. 슈퍼컴퓨터 수준이에요. 이게 이제 전 세계적으로 슈퍼컴퓨터의 랭킹인데 좀 오래된 데이터긴 해요. 네. 오래된 데이터긴 한데 10만 테라플롭스면 이 TPU 파드 하나면 10만 테라플롭스 하나면 네, 대략 한 4위, 5위 정도 되더라. 이게 제가 찾아봤는데요. 그러니까 최근 2021년 데이터를 찾아봐도 약 5위 정도는 하더라고요. 그만큼 이제 컴퓨팅 파워가 되게 좋다는 얘기죠. 그리고 최근에 이제 구글 I/O, 저희 이제 구글의 대표적인 이제 개발자 행사 구글 I/O에서 순다 피차이가 TPU 버전 4를 얘기했고요, 발표를 했고요. TPU 버전 4를 또 스케일러블하게 또 묶었어요. 8개의 파드를 묶은 거예요. 그러니까 8,000개의 칩을 묶은 거예요. 그랬더니 9 엑사플롭스가 나오더라. 앞서 봤던 10만 플롭스의 한 90배 정도 되겠죠. 네, 그 정도의 컴퓨팅 파워를 묶어서 저희가 만드는 구글 트랜슬레이트, 저희가 만드는 내부의 음성 인식 엔진들 이런 것들이 이 센터에서 이루어진다라는 얘기인 거죠. 그리고 이제 사실 이렇게 이제 리니어하게 성능이 증가되면 실제로 이제 머신러닝을 하시는 분들은 또는 이제 진짜 초고대 AI를 모델을 학습하시는 분들은 걱정이 사실은 하나가 있긴 있어요. CPU가 물론 하드웨어 스펙상으로는 이렇게 높다라고는 하지만 정말로 실제로 계산을 그렇게 할까라는 부분들을 고민을 하게 돼요. 그래서 이거는 이제 연구 논문에서 가져온 건데요. TPU를 6,000개의 칩을 엮어서 했었을 때 하드웨어 스펙상으로는 하드웨어 스펙을 만족한다면 100%가 나와야 되지만 그거보다는 조금 낮지만 약 50% 정도의 실제 성능을 내더라. 이거는 실제 해보면 통신이라던가 또는 학습 과정에 또 스케줄링의 문제이기 때문에 100%는 이론상 나올 수가 없는 거거든요. 근데 어쨌든 거의 다른 기존의 방식들에 비해서 50% 정도가 나올 정도면 실제로 하드웨어 스펙만큼의 성능을 낼 수 있다. 그래서 이런 걸 통해서 초고대 AI를 만들 수 있다라고 하는 얘기인 거죠. 그래서 현재 TPU는 다양한 분야에 보시는 것처럼 자연어 처리, 그다음에 이미지, 그다음에 스피치 레코그니션, 그다음에 요즘에 이제 핫한 분야죠. 멀티모달 그 머신러닝 모델에서 많이 나오는 뭐 자연어를 이미지로 뭐 이런 이제 그것들이 많이 나오는 이미지 생성 모델 저게도 많이 사용이 되고 있고요. 뭐 최근에 이제 뉴스를 들어보니까 그 이미지 생성하는 모델을 이용해서 만든 그림 작품이 미술 대회에서 1등을 했다는 얘기를 봤던 것 같아요. 그만큼 사실은 저는 솔직히 그렇게 생각했어요. 이미지 생성 모델이 그러니까 자연어 기반으로 이미지 생성 모델이 나왔었을 때 그 멀티모달 방식이 그렇게 나왔었을 때 그거를 과연 얼마나 쓸까 또는 얼마나 멀추하게 올라갈까 생각했는데 그게 거의 1, 2년 사이에 그렇게 뭐 미술 대회에 가서 수상을 할 정도라는 걸 보니까 생각보다는 우리 실생활에 되게 빠르게 적용이 되고 있더라라는 생각이 들었어요. GPT-3가 처음에 나와서 마케팅적인 얘기가 되게 많았거든요. 그러니까 GPT-3를 이용하면 뭐 예를 들어서 뭐 UFO가 어떻게 있는 거야 없는 거야라고 질문을 해도 답을 줄 수 있더라라는 식의 약간 버즈워드 같은 이런 것들도 많이 돌았잖아요. 그래서 그게 얼마나 이제 실생활에 쓰일까 저도 살짝은 이제 그 고민 내지는 이제 컨설을 가졌는데 실제로는 이게 활용되는 분야를 보니까 역시 인간은 위대하더라고요. 그 활용처를 잘 찾아가지고 정말 맞는 분야로 잘 적용을 하고 있더라고요. 그래서 TPU를 적용한 이제 국내 사례들이 몇 개 있어서 소개를 드리면 최근에 많이 이제 뉴스에 나왔던 게 LG AI 리서치에서 했던 엑사1이라고 하는 초고대 AI 모델이에요. 여기가 약간 3,000억 개 정도의 파라미터를 사용했다고 하죠. 물론 LG의 AI 연구원에 계신 분들이 주로 이제 많이 작업을 하셨지만 이런 초고대 AI를 만들기 위해서는 이제 자사의 인력들만 가지고 하는 것보다 여러 기관들 또는 회사들과 같이 협력을 해서 하는 게 좋기 때문에 구글을 포함한 여러 기업들이 같이 참여를 해서 이렇게 만들었고요. 그래서 이 엑사1을 이용하면 이런 것들이죠. 말하자면 뭐 엄마가 아이하고 동화책 얘기를 하다가 그 동화책 얘기를 딱 들려주면 그걸 이용해서 이미지를 만들어준다든가 우리가 상상하는 멀티모달 AI잖아요. 그러니까 초거대 AI를 이용했더니 그런 우리가 알고 있는 멀티모달 AI, 우리 실생활에 좀 더 밀접한, 내가 스토리를 들려주면, 내가 소설을 들려주면 음악을 만들어준다던가 이미지를 만들어준다던가 아니면 요리를 해준다던가 이런 식으로 발전을 하더라는 거죠. 완벽하진 않지만 그런 식으로 발전이 되고 있는 것 같고요. 그리고 또 질 수 없죠. 네, 카카오 브레인에서도 역시 이제 TPU를 사용해서 카카오 브레인도 역시 비슷하게 이제 엑사원처럼 멀티모달 AI를 지향을 하고 있는데 현재는 이제 자연어하고 이미지 쪽에 포커스를 해서 자연어 모델을 개발한 게 있고 최근에 이제 윈달리라는 또 그 이미지 생성 모델을 내놨잖아요. 그래서 그런 쪽에 TPU가 그 초고대 AI를 만드는 부분에 사용이 되고 있고요. 네, 마지막으로 네, 이런 이제 그 TPU 같은 기술을 통해서 AI 전문 칩이자 확장 가능한 이런 기능들을 통해서 국내에 조금 더 많은 초고대 AI가 나왔으면 좋겠습니다. 네, 이상으로 제 발표를 마칩니다. 감사합니다.
예, 좋은 강연 정말 감사드립니다. 이어지는 순서로 엘리 dob슨 그래피코 프로덕트 클라우드 부사장님 말씀을 들어보도록 하겠습니다. AI 기술을 통해 사람들이 더 건강하고 더 공정하고 더 지속 가능한 삶을 꿈꿀 수 있도록 돕고자 하는 그래피코 프로덕트 클라우드 엘리 dob슨 부사장님은 IPU 기술을 통해 기계지능의 차세대 혁신을 만들고자 노력하고 있습니다. 엘리 dob슨 부사장님의 말씀을 외국 현지에 계신 관계로 영상으로 만나 뵙도록 하겠습니다.
Annyeonghae Sai Yo. I'd like to thank the City of Busan, the Digital조선일보, International Association for AI and Ethics, Busan IT Industry Promotion Agency, and Busan University AI Graduate School for the opportunity to talk to you all today. I'm going to be talking to you about foundation models, what they are, how they're used, and how you can use them to help advance your business. I'm going to give a hardware perspective to that particular topic, as I work for a company called Graphcore, whose business is building AI accelerators that are purpose designed for AI problems. Large-scale AI is set for a paradigm shift. So I've worked as a data science practitioner out in the field for the last 10 years or so, and what I've seen in the last few years is that the landscape of AI has transformed dramatically. So how's it changed, and how do we expect it to change in the future? So first of all, right now, typically a custom model is used for each task and each data format. What I mean by that is if you want a model to make predictions around text, you would train that model on text data. And if you want a model to make predictions around image, you would train that model on image data. It's rare to see models that combine multiple data formats in the same format, although that is starting to happen now. And it's even rarer to see models that perform multiple tasks at the same time. Typically, models can only perform the tasks that they are trained to do. So how will that change in the future? We expect to see models becoming more general purpose. We expect them to be able to handle multiple data formats, so text and images, and other data formats as well in the same model. Image captioning is an example of early model iterations that are able to do that. We also expect to see general purpose models that can handle multiple tasks at the same time. So a model that doesn't just do the task that it is specifically trained to, but is able to handle multiple tasks within the same general purpose model. Another shift we expect to see is a shift from purely data-driven methodology to hybrid data and human reasoning. Many enterprises seek to replicate the success seen by hyperscalers in using large amounts of data to train very complex models to be able to do very clever things, such as the success that we have seen in Google and Microsoft and the like. However, the application of these kind of models to multiple industries may be more challenging. I come from a background of working in safety critical industry, and in that case, where there's safety involved, where there's legal implications involved, a human in the loop with the model is really paramount to have models that are widely adopted in those sorts of challenging environments. To do that, a model must be explainable. It must be able to explain not just what its prediction is, but also give surrounding context and be able to explain why it is making the predictions that it is, so that the model can work alongside a human to build these kind of hybrid systems. The most dramatic shift, in my opinion, that has happened over the last 5 years is the split of the AI value chain over multiple entities. Until fairly recently, the whole AI chain was owned by the same entity. By that, I mean that a company would own the data, a company would train the model on the data, the same company would put that model into making predictions, so by that I mean inference, and then they would use that to drive their own business decisions or offer that as an offering to their customers. That is changing. We now expect to see the AI chain split by who has access to the end user, the data, and the compute. The shift that we are already seeing is the rise of what we call foundation models, where one company who has access to a lot of data and a lot of compute, right now that is the hyperscalers, for example, Microsoft working in collaboration with OpenAI is the most famous example to date, where they train a very large foundation model that is starting to look like a general purpose model. That model can be tuned and tweaked by others to be able to serve their data and their customers. Finally, AI, particularly large-scale AI and foundation models, is still by many driven by exploratory research. We read in the papers how many parameter counts somebody has put into their model. State of the art is about 200 billion parameters in a single model. However, those kind of models, for most customers or most companies, is driven by their research departments and not their commercial departments. Commercially available APIs are very, very expensive, and at Graphcore we're hearing from many of our customers that these APIs are too expensive for them reasonably to be able to use and insert into their products. So going some more detail into some of those things that I've discussed. Today's research is tomorrow's commercial product. Like I said, looking at very large parameter counts, very large general purpose models, that is very much the domain of research. State-of-the-art research is looking up to about 100 billion parameter count mark and even beyond today. However, commercially, when we talk to customers about what they commercially are using in their production systems, powering their applications, powering their business decisions, they're talking more about the 2 billion parameter mark. That's a much smaller model. It's only slightly larger than BERT, which is typically the gold standard for NLP style problems. And these models are all dense transformers, especially the ones in the commercial space. By that, I mean that the model has all parameters are tuned with every pass, forward and backwards pass of the model. That can be very computationally expensive, and what you're effectively doing much of the time is you're multiplying by zeros, which is not an effective use of the hardware. That means that training these models can be very expensive. That in turn means that having these models offered to others as APIs, that can also be very expensive. Research are looking at combining multiple data formats and multiple tasks into the same model. We are now starting to see commercial implementations of multiple data models. So for example, combining images and text in the same model, we're starting to see those become commercially available. However, we are yet to see true multitask learning models which are in production and used in commercial settings. That is still very much the domain of research. So what do we expect to happen in the future as we go from left to right on this slide? Well, the biggest shift that we expect to see is we would expect the parameter count to go up to about 1 trillion parameters in the future, where 500 trillion parameters is considered to be brain scale and human level AI. There is a big problem with scaling parameter counts to that level, and that is that training these models and using these models, putting them into an inference setting, is effectively cost prohibitive for most, for all, I would say, to be able to really scale a model up to 500 trillion parameters in brain scale. So in research, people are increasingly exploring conditional implementations of models. That means where you're not updating parameters where you don't need to. You're not spending a lot of hardware time multiplying zeros by zeros. And so that comes under a lot of names, but when people talk about sparse implementations, conditional implementations, I believe Google call it pathways, that's basically what they're referring to, which is the most efficient use of model parameter updates, which results in a more cheap implementation of these very large models that have very, very high accuracy. So to say a little bit more about what do I mean when I say the ecosystem is going to split. So we think that the ecosystem is going to be split into three. Who are those three different players that we see in this market? So there's number one, which is the pre-trainers. They take very, very large amounts of data, for example, videos, code bases, large text corpuses, large amounts of images, and they train very, very large models. And by that I mean models with very large parameter counts to make the model that they then want to pass on to others. That's very expensive, it takes a lot of time, and possibly most importantly, it takes a lot of compute, which means that these companies that are pre-training these ultra-large foundational models, they need access to very large amounts of hardware. That's typically the hyperscaler market. We also see it for national labs, so government-funded research bodies, for example, are often very interested in building their own language models. So not just an English language model, but a Swedish language model or a Korean language model, or whatever language they want to train is something that we often see in national research labs. So when that model is trained, what does that customer then want to do with it? Well, they want to expose that as an API, or they want to use it for their own uses. If they expose it as an API, they can do two things. They can allow others to download that model and put it into production and use it for their own use cases, or they can offer it as an API, which OpenAI is doing, where people can subscribe to the API, ask the model a question, and get an answer back. We've seen both. So what are these people doing with these models? Well, this is the market which I would refer to as the adapters. So this is the smaller enterprise market. They have data. Their data is their IP because their data concerns their customer base, and it will help them build models which will allow them to understand their own use cases and their customers better. So the data is very often proprietary. The issue is the data set that most enterprises have that is their own data and is proprietary. The data set can often be small, maybe it's unlabeled, maybe it's poor quality. And so it's been hard for them to build their own models from scratch using that fairly small and poor quality data set. However, if they can combine that data with a pre-trained model that is pre-trained by somebody else, such as Microsoft, they can build a much more powerful model, and that's now what we're starting to see, in that we're seeing smaller enterprises fine-tuning or adapting. Sometimes people refer to distilling or adaptation of that model to make their own custom model, which is specific to their use case, specific to their vertical, and specific to their customers. Once they have trained that model, they would then put it into production in an inference setting, and that means when you put the model so that somebody may ask it a question and it will provide an answer. So for example, chatbots is a very common example that we see, image caption, content generation, and all the use cases of AI that we're used to seeing by this point. So what will the challenges be? Well, the biggest challenge is going to be expense and access to hardware. Not everybody can afford large accelerator clusters. Even if they can, they're very expensive. And most of all, they do not scale up to brain scale. If you want to train a 1 trillion parameter model on 1 trillion data items, that's getting towards brain scale. It's expected to take about 1,000 chip years to be able to do that. So that's 1,000 years for a single chip to train a model to that scale. It's too expensive, it's too power hungry, and it's too time consuming. That is the biggest challenge in the pre-training market. So the model type needs to change to allow more effective model architectures to come onto the market. However, running these is hard on conventional hardware. Conventional hardware is not built to look at more conditional or sparse implementations of models. They do very well on dense transformer models, but they do not do so well on newer types of new model types, which might make a better and more efficient implementation. The latency can be challenging for very large models. If you want a chatbot which can chat in real time, it can be challenging to get that chatbot to reply in a time and an accuracy that is suitable and fit for purpose for a chatbot setting. Finally, programming large models is very hard and time-consuming. It's a very niche task, and hiring people who are able to efficiently program large models can be very expensive. They are also a rare resource worldwide. So we believe that a new general purpose solution is required to solve these problems. And we believe that the solution will need 4 things. The chip will need to be designed to efficiently handle regular data and compute. We believe the memory hierarchy and interconnect should be designed for cost, performance, effectiveness at scale. The systems that house the chip need to be designed to easily scale to supercomputer scale to handle the very large parameter counts that we expect to see in the future. And finally, they need to be programmable. They need to both be programmable so people can quickly build and experiment with new model architectures, but they also need to be explicit, allow explicit implementation to performance optimize the models that programmers may want to run. More on that later. So on the chip itself, this is the chip that at Graphcore we have designed and built, that we have built to handle models that will ultimately evolve to conditional and general purpose implementations. What are the features of this chip that make us believe that this is a suitable solution for these kind of models? So first, it's MIMD, meaning multiple instruction, multiple data. We believe this is a key feature needed for irregular and multimodal architectures and data that needs on-chip task parallelism. Secondly, software-controlled data movement, which allows efficient communication within the chip, which is particularly important when you're running very large models and efficiency is paramount. Low precision, we don't believe that high precision is needed for these kind of computations and is redundant and effectively just wastes power and wastes compute. And finally, on-chip random number generation, because these models are fundamentally stochastic in nature. Our chip is also programmable with rich automation, so we believe that the future is an open source for being able to program these kind of models. The 2 front runners right now are PyTorch and TensorFlow. We're increasingly seeing customers also asking for JAX, and there's obviously a lot of libraries which sit on top of these main frameworks, which is crucial to be able to support developer teams who are trying to program these models. We think that out-of-the-box capability where possible is very important given the price, the price of spinning up a team with developers who are able to program these kind of models, but also we believe flexibility where the models can be decomposed in a parallel way so they're able to split a model over multiple systems, multiple chips, over multiple dimensions. So our next generation solution, which we're calling the good computer, will allow AI models to be developed with 500 trillion parameters. GPT-3, which is currently the gold standard for large models today, we can run full pre-training for that in less than 3 days, and we can run inference at more than 100 tokens per second per conversation by our forecasts of what this computer will allow. We expect that large models can be written in standard frameworks that run out of the box without needing special parallelism libraries or modification. So in conclusion, we believe that AI models of the future will become larger, they'll become more complex, and they will be split between commercial entities. Smaller enterprises can make the most of this shift by targeting fine-tuning workloads and adaptation built on top of pre-trained models, which will be provided by the larger entities, the larger companies who are running the pre-training. And we believe that we have built a solution that meets the challenges of this new paradigm. Firstly, the chip, the memory hierarchy, and the system have been designed to efficiently handle irregular data and compute at scale. Secondly, a programming framework has been designed to balance the needs of explicit implementation and rich automation. And thirdly, this is available as a cloud-based offering already for running these large model workloads. So in conclusion, thank you. 감사합니다.
AI 기술 패러다임이 어떻게 변화할지 그리고 어떻게 새로 미래를 만들어 나갈지 들어볼 수 있는 좋은 말씀이었습니다. 감사합니다. 다음은 벤 게르첼 오픈코그 파운데이션 회장님의 강연을 들어보도록 하겠습니다. 차세대 인공지능으로 기술로 꼽히는 인공일반지능의 선구자인 분이신데요. 예. AI 시대의 보안 이슈 분석이라는 주제로 오늘 중요한 말씀 다시 한번 들어보겠습니다. 현지에 계신 관계로 영상으로 듣도록 하겠습니다.
This is Ben Goertzel. I'm the CEO of SingularityNet, the leading blockchain-based platform for decentralized coordination of AI. I've been working on artificial intelligence from both a research and application perspective for more than 30 years now. And I want to talk to you a bit today about issues at the intersection of AI and security, and about how standards bodies and standardization initiatives can help, ensure AI security is more and more of a reality than just a pipe dream. We're living at an incredibly exciting time for the artificial intelligence field. Between 2014 and 17 or so, we saw computer vision exponentially accelerate in its capabilities and correspondingly its practical utilization. Between 2017 and now, we've seen natural language processing similarly explode and move from being a research area to being a major part of the global economy, and something that actually works, right? And sometime not too long from now, we're going to see a comparable burst of progress, perhaps a few years long, in artificial general intelligence, the creation of machines that can think like people, or ultimately even better than people. And once we get beyond narrow AI applications, which we're seeing now across a host of vertical markets, once we get beyond these narrow AI applications, further and further toward general intelligence, the critical nature of security for AI will be even more abundantly clear than it is now. I mean, AI is starting to take over the world economy. AI is starting to verge toward general intelligence. Now is when we want to get the security aspect of AI down pat before the next part of the revolution happens, because we don't want the breakthrough to AIs that can really think like people or are smarter than people. We don't want that to be co-opted by people hacking into the AGI's brain, or by the AGI being buggy and doing totally different things than it was designed to do, right? So I'm sharing my screen, and what I'm showing you here is a few of the key aspects that need to be handled adequately to have AIs that are secure. And this is a bit of a scary list, because there's a lot of big things on here. The good news is these are all things that we basically know how to handle in concept. The last good news is that the AI field as a whole is not doing an especially awesome job of focusing attention on these things. So taking from the top down, value systems, what are our AIs trying to do? What functions are they trying to maximize? What purposes are they trying to serve? Architectures, which ways of building an AI can really work to achieve the values that we want. Transparency, how can we how can we make sure that AIs can communicate to us at least some approximation of what they're doing and how they're working? Why do they come to the conclusions that they do? Control and ownership. I mean, who owns the AI? Who's manipulating it? Who's watching it? Formal verifiability. Can we do the math to actually show that the AI is fulfilling its specification, or are we just leaving it up to chance and to the the normal software engineering and debugging process, which we know always lets major bugs through? If we have decentralized control rather than a centralized party controlling our AI, how do we make the collaboration among the distributed decentralized parties that are jointly controlling the AI? How do we make that actually work in a scalable and secure way? How do we build security into the network plumbing underlying the AI's operations? So this is a bunch of big issues. I'm gonna go through these issues at a high level now, and then I'll talk briefly about how standardization and the action of standards bodies could help a bit with bringing these things about, along with a whole bunch of other coordinated activities. So let's start with value systems, right? I mean, value systems is a hard enough thing for humans to grapple with. The scope and diversity of human value systems is tremendous, right? And what I think is good, the average person in, say, Saudi Arabia, Congo, or Japan might not think is actually the best, and vice versa. And human values change over time quite rapidly. I mean, what was considered highly desirable in 1500 is not quite the same as today. Even in my youth, values in America were quite different than today. And I think to deal with this dynamic nature of values, we have to articulate core value systems for AI: compassion, growth, joy, free choice. Then we need to talk about specific and culturally dependent value systems, which are going to change rapidly over time. We then have to give our AIs the ability to rapidly adapt their detailed value systems as culture evolves and as their setting evolves. They have to be able to rapidly adapt their detailed value system consistently with their core value system. This is a challenge for people. Could be that AIs are better than this than people ultimately. I mean, they can introspect into the depths of their minds better than people can, and they in some ways can be less hung up on their ideas than people are, and more adapted. But there's a lot of work to be done there, and much of this work is in the area of AI architecture. I mean, not all AI architectures are consistent with all value systems, right? A lot of AI systems now are focused in reinforcement learning, where they're trying to maximize the expected reward according to some reward function. And it's not clear how consistent reward maximization is with the fundamental value of compassion. In a way, reward maximization is intrinsically selfish and self-focused. It's based on each agent maximizing its own reward, right? And it could be that you need a different approach to motivation to encompass AIs that can really fundamentally listen to others and have sort of I-thou bonding experiences with others. And I mean, this is subject for experimentation, but we don't see that much experimentation on this right now. The intersection of AI architecture with value systems is almost an untouched area of research, right? AI transparency, AI explainability is getting a lot more attention right now, but a lot of this attention is quite naive. Many people in business, in the financial industry, for instance, are they're still thinking that you can actually make an AI that will explain all of its thinking and reasoning about things to people. But, the bottom line is a human can't explain all their thinking and reasoning about something to other humans. And AIs won't be able to either. The reasons for an AI's judgments are going to be very, very detailed, complex, and involved. And what they will be able to do, as many of us humans can do, after they make a judgment, after they think something through as a separate cognitive process, they'll be able to come up with an explanation of that thing. And explaining what you're thinking is actually a separate intelligent process than doing the thinking originally. Some humans are good at thinking and bad at explaining their thoughts. Some humans are mediocre at thinking, but very good at explaining their thoughts. And this can be very, very important. So we need to address explainability. We also need to understand that explainability will only be partial, right? And this means there, in the end, has to be some trust in whoever wrote the explainability software. And trust is pervasive to the different points I'm making here, right? There's trust in the AI's own processing. Then there's trust in who owns the AI and who controls the AI. And seems that in the end, the only really secure and defensible mode of AI control and ownership is decentralized AI control and ownership. A single point of failure owning and controlling AI just has, there's too many well-known risks there. Decentralized control of AI requires a variety of different protocols, right? Many of which are being worked on in the SingularityNet ecosystem that I'm leading. You need protocols for decentralized compute resource sharing, which is dealt with by NewNet.io. You need integration of the APIs of different AIs for mutual AI cooperation, solving problems for AIs outsourcing work to AIs that outsource work to AIs, which is what SingularityNet protocol deals with. You need secure core decentralized messaging underlying this network, which is what the hypercycle project that I'm working on with Tufi Saliba is dealing with. So you need all these things, and NewNet, SingularityNet, and hypercycle are dealing with parts of these, but there's a lot of other parts too. Blockchain technology is part of the infrastructure here. It's just barely up to the task at the moment, but we're making it better and better in projects like SingularityNet, hypercycle, Cardano, and a bunch of others. Cardano, which is one of the leading blockchain networks out there, which we're working with closely on SingularityNet, has also been leading the way in another key aspect of AI security, which is formal verification. Ideally, when you've written some software code, you'd like to have a clearly written sort of logical specification of what that software code is supposed to do. Then you'd like to be able to prove using an automated theorem prover, a formal verifier, that the code does what the specification says. For example, Cardano's core Ouroboros consensus mechanism has been formally verified. Not much else in the commercial software world has been, but I think ultimately we need our core communication and collaboration protocols and our core machine learning and reasoning algorithms to be formally verified by automated theorem provers, ultimately AI-guided automated theorem provers, or else we're going to find our security is compromised by bugs in the AIs, right? And this ties in with the need for secure, distributed, and decentralized collaboration on AI problems. So once we have decentralized AI networks and we're verifying that they're doing what they're supposed to be, we next need to address the issue that not everyone on that network is going to trust everyone else on that network with their own data or with knowledge of their own, partial conclusions or even with the questions that they're asking. So we have technologies like multi-party computing and homomorphic encryption, which help to deal with the issue of secure, distributed, and decentralized computing. But then, then people have to ultimately trust whoever wrote the code for the multi-party computing or the homomorphic encryption, which really comes down to formal verification of these secure, distributed, decentralized computing methods again, right? And then, of course, people need to trust whoever wrote the formal verification software, which in the end has to come down to reputation of whoever wrote that software, reputation then coming down to design of decentralized networks for assigning reputation. There's a lot of interesting interoperations between these aspects. And finally, all of these things are running on computer networks. And right now, the core plumbing of our computer network, stuff like TCP/IP, which is great for what it does, but this doesn't bake in security into the plumbing of the network, right? And it kind of couldn't way back when TCP/IP was invented because it would have just been too slow given the networks of that time. But now, with modern networks and modern processors, we can move to a new generation of networking APIs that have security baked in, and that this is going to be critical along with all these other higher level aspects. So let me go back to sharing my screen again, and I just want to talk a little bit about how standards bodies and standardization potentially can help with each of these areas, which is critical to security of AI networks going forward. So regarding value systems, this might seem a nebulous thing that can't be standardized or formalized, but actually my oldest son, Zarathustra, gave a talk a couple weeks ago at the AI for Theorem Proving conference, AITP 22. You could find his brief talk online, but he outlined some work being done during the last few months using the Sumo ontology and the vampire automated theorem prover to try to actually prove things about ethics, about the relations between different value systems. So you can actually formalize value systems and ethical principles in mathematical logic, and you can prove things about how ethical a certain AI system will be in certain scenarios given certain assumptions, right? So it's not easy, but it's actually formally tractable. And the design of AI architectures as well. I mean, an AI architecture like the OpenCog Hyperon architecture I'm working on with my team at SingularityNet and OpenCog Foundation. I mean, this is a big complex thing, but you can specify what properties you want an AI architecture to have in terms of, for example, the ability to have compassion, the ability to model other minds, the ability to adapt its value systems based on context. You can formally express what properties you want an AI architecture to have, and then you can verify whether an architecture fulfills those properties. Right? It's not easy, but this is all susceptible to verification. And then the properties that an architecture should have can be part of a standard, just as the value systems that they should have can be part of a standard. All this can be written down, discussed, agreed upon, and standardized in a perfectly tractable way. It just takes some thought and attention. And the same holds really for transparency and explainability. We just need to standardize what level of explanation is needed. What explanation language should an AI use to explain itself? You know, how accurate does the explanation need to be in terms of all the stuff the AI is doing inside, you know, based on the domain and the particular problem being solved? Decentralization in networks. I mean, how decentralized is a network? The Cardano community, in their context, has done a good job of quantitatively measuring the decentralization of their network as it increases. You can see that in that sense, it's much more decentralized than, say, Bitcoin, the classic cryptographic network in some ways. Yet in other ways, Bitcoin is more decentralized. There's multiple ways to measure decentralization. We don't need to pick just one, but we can provide a library of different measures of decentralization, of control and ownership, right? And next on the list, formal verifiability is sort of easier to establish as a standard. You can have a collection of approved theorem provers, a way of approving a theorem prover, and then collection of approved formalization languages for the specification of what an AI system does. Then you can simply require that AI algorithms, AI implementations carrying out critical functions can be formally verified by one of the approved theorem provers according to a spec expressed in an approved way. I mean, it's not how the software world works right now. It's not how the AI world works right now. It's totally feasible and plausible, right? And to bring this sort of formal verification to the decentralized world, you can do like we're doing in SingularityNet and make a formal language. This is our AI DSL, AI domain-specific language. You can make a formal language for interaction between AIs in a decentralized network, which lets the AIs, you know, find other AIs they can cooperate with using the formal query language, and it also lets you formally prove things about the joint action of all the AIs in a distributed network, right? And then if all these AIs are running on a secure underlying protocol with formally verifiable properties like the TOTA protocol that we're baking into our hypercycle network, and if the encrypted interactions of these AIs are taking place using, say, multi-party computing or homomorphic encryption schemes that are formally verified and are operating on top of this formally verified secure network protocol. I mean, in the end, you have a whole AI stack from the network protocol up to the decentralized interoperation layer and the ownership within that decentralized layer, up to the AI architectures and algorithms and how they explain themselves and the value systems that these AI systems are using to guide their actions. We can do all this in a secure, fully standardized, fully formalized, verifiable way. It's hard, but it's not any harder than a lot of other things that are being done in the technology world. Right now, it's really just a matter of focusing attention on it, which I've been doing with my colleagues at SingularityNet and OpenCog and Hypercycle, and which I'm hoping, the folks listening to this talk can help with moving more and more of the AI world toward focusing attention on these critical security issues that we really need to solve better if we want the artificial general intelligence revolution to unfold in a safe way for everybody's benefit. Thank you.
네, 여기까지 듣겠습니다. 인공지능 기술의 위험성과 거기에 대한 윤리 기준 그리고 안전성에 대해서 좋은 강연이었던 것 같습니다. 다음 강연은 라일라 트레티코프 마이크로소프트 부사장님의 강연입니다. 인공지능 인지 능력과 혼합 현실 연구를 통해 실제 디지털 세계와 디지털 세계를 조화롭게 혼합하고자 노력하시는 분이신데요. 이분께서 AI 보안 및 윤리의 올바른 적용에 대해서 적용을 주제로 강연 이어주시겠습니다. 역시 현재 거신 관계로 화면으로 만나보시겠습니다.
Hello, everyone. It is an honor and a privilege to join all of you here today at IEEE conference on AI in Korea. I think it is obvious that AI progress and its adoption are accelerating, and the expectations are also growing. Some are real, valid, and others can be sensational. Just a few days ago, these headlines ranged from AI taking over voice acting from James Earl Jones, the voice of Darth Vader in Star Wars, to Alzheimer's scientists calling for AI to fill in the gaps in brains of dementia patients. There is no question AI is becoming ever more powerful and more in demand. Just look at a few highlights of products here. But it also appears ever more mysterious to many of us who are not close to it, even if we're engineers, and thus it is deeply misunderstood. At the same time, AI is becoming more integrated into our lives. Often this happens quietly, without users even noticing. How often do you question why certain messages appear for you in your social media feed? Why are you seeing one ad, but not another? Cutting-edge technology is not staying in the lab. More and more AI is being put to work in applications that affect us as individuals and as members of society. With this level of proliferation, there are new headlines highlighting concerns regarding the use or misuse of AI. Societal expectations are growing. More members of society are considering whether AI is trustworthy and which companies are innovating with their concerns in mind. At Microsoft, we have worked on AI for decades, exploring what is possible long before it entered the mainstream. We learned a lot along the way. Advancements in AI are fundamentally different from those in general tech. First, AI's proximity to human intelligence, while powerful, also makes it vulnerable to embedded social biases and harmful exploits. Second, AI can handle amounts of data and levels of complexity that exceed human capabilities. Its intelligence is fundamentally different, making it difficult to explain or even understand as we were able to do with traditional symbolic systems. The pace of innovation is faster than what we have seen before or even predicted, thanks to the immense scalability of AI. Just to give you an example, some of us might remember that 30 years ago, every business was looking to software to redefine its operations. New systems of records, or databases as most of us know them, were developed and deployed to manage every core process in enterprise, from accounting to payroll, resource planning, and customer management. This change was foundational for the digital transformation. But as big of a change as it was, the digitization of the core processes didn't alter the primary business of the company. It just made it more streamlined, a bit faster. Contemporary users look at software and digital devices as irreplaceable parts of their lives. Companies, even in traditional industries, look at software as something that is infused through every aspect of their business. Nowadays, every company is a software company. Digitization of the world has also had a secondary effect: the proliferation of data. Systems of records transformed and aggregated user files into digital stores. New applications added a vast amount of engagement data about product usage and customer interactions. This created the perfect environment for AI. AI is not just transforming, it is disrupting what we thought was possible. The vast amount of data generated in the previous decades provided the fertile soil needed for AI to grow, to learn and organize knowledge obtained in that data into a mathematical model used to create insights that previously were outside of our ability to compute. This can give us an order of magnitude return on our effort, or make things possible even in the first place. As the technology improves exponentially, allowing us to compute more data than ever before, and new systems of information join this network, even more so with IoT-enabled devices, it is imperative that we think about the use and impact of the technology and artificial intelligence on society. And because of this, it is imperative that we, technologists, engage deeply in the responsible development and use of AI that prioritizes people at the center to accelerate positive outcomes for businesses and society. We start with values and principles for ethical AI's use. We adopted these in 2018. 4 core principles of fairness, reliability and safety, privacy and security, and inclusiveness, underpinned by 2 foundational principles of transparency and accountability. All of these principles are here to safeguard our users and customers from unintended vulnerabilities of technology. As we build products, we must contend with difficult questions across the company on a daily basis, brought up by AI innovation. We come back to our principles time and time again to help us make decisions. Our principles are our North Star. But we do recognize that principles alone are not enough. They're not self-executing. Your desire and belief that an AI system should be fair or inclusive does not make it so. Principles are also open to interpretation. If I asked everyone in this forum what fairness means, we're likely to get as many different answers as people here. Principles also do not answer the question of how. Let me walk you through one example of how we worked through a challenging ethical AI problem and implemented our responsible AI principles in practice. A few years ago, we developed the ability to generate a synthetic voice of anyone using a remarkably small set of voice recordings. To train an AI that sounds like me, who is speaking, I wouldn't need a professional sound booth. YouTube videos will work just fine. And these realistic voice fonts can be used in high-value customer scenarios, from storytelling to branded bots to even helping those who have lost their voices. You may have heard about Anthony Bourdain documentary last year, where a portion of his voiceover was synthetically generated. But once we developed this technology, we quickly realized that we need to slow down, think through impact of this technology on everyone involved, and put meaningful safeguards in place. We were faced with the fact that the technology radically changes the paradigm for both creation and perception of speech. It represents a tipping point. Not only can digital likeness replace the human voice, but it can further diverge from the original, express and emote in ways that we weren't present in the original source material. The consequences can be enormous. We knew that we needed to simultaneously protect our listeners from misleading content and experiences, and protect speakers from having their voices impersonated or improperly used. The team began by interviewing voice actors to understand the impact to their labor market. They heard concerns about the impact to jobs, concerns about malicious use, the need for a verification mechanism, and the desire for more transparency about the capabilities of these technologies. Voice actors were also interested in how the technology would be used to scale the amount of work they could do and increase the ways that they are compensated. The team also worked with security experts to better understand the synthetic data ecosystem and potential risks. And they consulted with our Human Rights Council to understand broader societal impacts of this technology. They completed a thorough impact assessment. It's something we do at Microsoft on all of our AI technologies. That includes an examination of benefits, risks, and considerations of harm of this tech if this tech became broadly available. This was an opportunity to think about all the ways this could go wrong, be misused by itself or even in conjunction with other technologies. And using this very inclusive process, They then developed a mitigation framework that builds on distinct terms of use specifically for this service, a gating process for customers to gain access. They have to apply for use, and the scenarios are reviewed with our ethical panel. Consent and disclosure requirements on both sides for the listener and the speaker. We require that they receive information about how technology works and so they can meaningfully consent to its application. A code of conduct for the customer, and approved use cases, and even use cases that are forbidden. The team then broadly shared the approach to set the industry bar, because we were starting to see other companies put their speech out there without any guardrails. And recently we've added code-enforced mitigation, such as voice verification. A verbal consent file is matched against the voice actor in order to unlock the service. It is a challenge to bring together many diverse voices, experts, and those that are impacted by this technology in order to deliver technology with minimum unintended consequences and risks of harm. To make it easier for others, we're building tools into our AI platforms that make it easier for engineers, ML researchers, data scientists to build AI responsibly. This isn't only a technical problem, so tools alone aren't sufficient for responsible AI without the broader culture and practices. But innovative tooling helps our engineering teams to diagnose, understand, and mitigate issues in partnership with the broader set of stakeholders. Here are some examples of how we put this into practice. All of these are rooted in the ethical AI principles we discussed in the beginning. Machine learning teams deploy models in the real world, but they often face challenges of conducting rigorous performance evaluations and testing for AI models. How many times have you seen articles in the press that mention that the AI model is 90% accurate, using therefore a single score accuracy number to describe performance of the whole benchmark? The challenge here is that the aggregate performance metrics can hide important conditions of failure where the model may be underperforming, either for a particular input condition or for some population group. They give the impression that model accuracy is uniform when we know in real world it is not. We have seen unfortunate examples of this mode of failure in the press in case of unfairness due to model bias, where faces of one ethnic group may not be recognized as well as another, or lack of reliability and safety due to adversarial attacks, where a traffic sign detector fails with certain unexpected inputs. Even with overall accuracy of the model being high, it is still important for the development team to know ahead of time about the fact that the model may not be as reliable in some situations and what those situations are. Discovering pockets of data with high error discrepancy can be a tedious and time-consuming process, and it requires a streamlined infrastructure for error detection. Error analysis is one of many tools we're building into our ML suite, so we can give ML practitioners the ability to responsibly build AI. We're building and integrating tools to make sure we can identify, diagnose, mitigate, and protect a variety of responsible AI issues, because AI systems are vulnerable to new cases of failure, including security breaches, every day. Let us take a look at just a few. Researchers at the University of Cambridge and University of Toronto were able to trick a commercial machine translation system by using Unicode homoglyphs, which are characters that look visually similar, but actually are completely different characters to the algorithm. This is an example of an evasion attack. An evasion attack happens when the network is fed an adversarial example, a carefully perturbed input that looks and feels exactly the same as an untampered copy, but that completely throws off the classifier. Evasion attacks exploit the imperfection of a trained model. For instance, spammers and hackers often attempt to evade detection by obfuscating the content of spam emails and malware. Samples are modified to evade detection, that is, to be classified as legitimate when they're not. In a data poisoning attack, attacker corrupts the very training data used by the ML system. Here's a stop sign that looks like a speed sign to an image recognition system. But if you look closely, the stop sign has a little yellow post-it note on it. What the researcher did is included a fraction of images with stop sign with a yellow post-it note as a speed limit. The ML system learned that, and anytime it sees a stop sign with yellow post-it note, it now thinks it is a speed limit. Backdoor attacks are a special type of data poisoning in which the adversary implants visual patterns into the training data. After training, the attacker uses those patterns during inference time to trigger specific behavior of the target ML model. Model inversion attacks privacy. It uses available observation of the output to determine the set of input parameters. In other words, the original data used in training. That maximizes the predictive potential of a model. The importance of model inversion frameworks can hardly be overstated, considering that they establish a direct connection between models and the real world. For example, membership inference attacks use different methods to trick the target ML model to reveal its training data. If the training data included sensitive information, such as credit card numbers or passwords, these types of attacks can be very damaging. And of course, ML at the very end is just software. So normal software vulnerabilities apply. Here's the list of vulnerabilities for a very popular ML library. You can see the amounts are growing every year. So to wrap it all up, here are some possible harms within the AI lifecycle, which can have serious effects and create significant harms. Meanwhile, the stakes are high and are rising as the AI adoption is spiking across industries. Tackling AI security requires a system-level perspective, involving every member of the team from data science to DevOps. Right now, knowledge on secure AI is low across most engineering teams. We will need to help teams take a system view on ML. Ensure you empower ML engineers to develop and deploy their ML systems securely. Empower auditors to complete AI governance tasks. Empower security analysts to detect, respond, and remediate threats to ML systems. Push to develop best practices and standards across the organization and across industry. And live your principles across practices, tools, and teams, in your own companies, in your organizations, in your governments. IEEE can make a difference in where AI research is focused and drive standards to enable AI developers to build safe AI and best practices on how to deploy models to protect models against misuse. These are many ways we can think of to make AI more secure, less vulnerable to attacks or hijacking, because the impact of this technology will be greater than anything we have seen in digital to date. Thank you for inviting me.
네, 좋은 강연 감사드립니다. 여러 연사님들의 훌륭한 강연을 듣다 보니 어느새 오전 시간이 훌쩍 지나간 것 같습니다. 원래 강연 중간중간마다 쉬는 시간이 쭉 있었는데요. 영상으로 강연이 진행되다 보니까 조금 빠르게 진행을 해서 바로 점심시간을 진행을 들어가도록 할게요. 오후 세션에는 디지털 헬스를 주제로 국내 전문가분들의 현장 강연과 좌담회가 이어질 예정입니다. 여러분들 많은 참여 부탁드리겠고요. 잠시 후에 12시 50분부터 오후 세션 이어서 진행하도록 하겠습니다. 점심 식사 맛있게 하시고요. 오후에 다시 뵙겠습니다. 감사합니다.